Welcome to This Explainer. I am so thrilled you're here today because, well, we are embarking on a truly fascinating journey into the absolute foundations of geometry. Whether you're seeing this for the very first time or you're a seasoned math enthusiast just brushing up on your skills, the elegance of what we're about to cover is simply undeniable. Today, we're locking our focus squarely on Pythagoras' theorem, its brilliant converse, and the fundamental rules that classify triangles by their internal angles. Get ready, because by the end of this, the way you look at shapes is going to fundamentally change.
Okay, let's dive into this. Here's our roadmap for today. We'll hit the core Pythagorean theorem, look at finding missing side lengths, solve some complex polygon puzzles, explore the converse of Pythagoras, and wrap up by classifying triangles by their angles.
First up, Section 1, the core Pythagorean theorem.
So, what is this famous rule? Pythagoras' theorem states that in a right-angled triangle, the square of the hypotenuse length equals the sum of the squares of the other two side lengths. The equation you absolutely need to burn into your memory is c squared equals a squared plus b squared. And listen, it is incredibly vital to remember that c always represents the longest side of the triangle, which sits right across from that 90-degree right angle. We call that longest side the hypotenuse. Now, what's really interesting about this concept is how perfectly the math translates into physical space. If you look at a right-angled triangle bordered by three distinct squares, you'll see something amazing. The area of the large square drawn on the hypotenuse physically equals the exact area of the other two smaller squares combined. It's not just some abstract set of numbers on a chalkboard, it's a physical, geometric truth. If you were to literally cut up the two smaller squares, those pieces would perfectly fit into and fill the space of the largest square. That physical certainty is exactly why builders, engineers, and architects have trusted this very math for centuries to keep structures perfectly aligned.
Let's put this into action. Section 2, finding missing side lengths.
Take a look at this first example. Notice how this theorem acts like a universal key. Whether you're calculating the length of a roof truss or mapping a shortcut across a rectangular park, this is your go-to tool. In one scenario, you might be given two shorter sides, say 15 centimeters and 20 centimeters, and you need to find the missing hypotenuse. But in another scenario, the whole thing is flipped. You might know the hypotenuse is 5, you know one side is 4, and you have to find the missing shorter side. The absolute beauty of c squared equals a squared plus b squared is that it seamlessly solves both of these scenarios.
To nail this efficiently every single time, first things first, always identify your hypotenuse. If you're solving for the hypotenuse, you just set up your formula. Say your shorter sides are 15 and 20. Your setup is x squared equals 15 squared plus 20 squared. Next, square those knowns, which gives you 225 plus 400. That equals 625. Finally, you just find the square root of 625, giving you a crisp, clean 25. Now, what if you're finding a shorter side instead? Well, you just isolate x squared by subtracting the known square from the hypotenuse square. So, if your hypotenuse is 5 and a side is 4, you do 25 minus 16, which is 9. And the square root of 9 is 3. Honestly, it's algebraic perfection.
Time to level up. Section 3, solving complex polygon puzzles.
Let's tackle a slightly trickier puzzle. Imagine a polygon made of two joined right-angled triangles, and the goal is to find its total perimeter. Now remember, perimeter is just the distance around the outside edges, so we need all the outer side lengths. Let's say we have 3 of those side lengths of 4, 3, and 13, but one outer side is completely missing, and to make matters worse, the middle dividing line inside the polygon is also entirely missing. So how on earth do we find the outer edge when the internal structure itself is a mystery?
The secret lies in breaking the shape down. It's like a domino effect. Solving one triangle brilliantly unlocks the exact missing piece you need for the next one. First, you focus purely on the first triangle. Using our theorem, 4 squared plus 3 squared equals the hypotenuse squared. That's 16 plus 9, which is 25. The square root of 25 is 5. Boom! We've just found that missing internal dividing line is 5 centimeters. Now we pivot. We use that brand new 5 centimeter line as a known base for the second triangle. To find the missing outer side, we do the math. 13 squared minus 5 squared, that's 169 minus 25, leaving 144. The square root of 144 is 12. Finally, we just add all the outer sides together. 4 plus 3 plus 12 plus 13, giving us a final perimeter of 32 centimeters. It's a truly satisfying puzzle when you solve it step by step.
Now for a geometric plot twist. Section 4, the converse of Pythagoras.
The converse states something super interesting. If the sum of the squares of two side lengths of a triangle equals the square of the third side length, then the triangle is guaranteed to be right-angled. In plain English, we're no longer assuming it has a 90-degree angle to find a missing side. Instead, we already know all three side lengths. And if the math perfectly balances out, it mathematically guarantees that a 90-degree right angle exists exactly opposite the longest side. Carpenters and builders actually use this trick every single day. They call it the 3-4-5 rule to guarantee a room's corners are perfectly square before they even start putting up the drywall.
And this brilliantly illustrates the core difference between the two concepts. With the original theorem, you start with the knowledge of a right angle, and that allows you to confidently use the formula to find missing sides. But the converse flips the script entirely. You start by proving the formula works for the numbers you have, and that result acts as an irrefutable tool to prove a right angle actually exists.
Let's look at how you might use this in a practical example to prove an angle is 90 degrees before calculating area. Imagine a triangle where you know all three sides are 15, 12, and 9, but you have no idea if it's a right-angled triangle. To prove it, we test the math. Does the longest side squared, which is 15 squared, or 225, equal the other two sides squared? Let's check. 12 squared is 144, plus 9 squared, which is 81. 144 plus 81 is exactly 225. Because both sides perfectly equal 225, we have just proven with absolute certainty that this triangle has a perfect 90-degree right angle. And only after proving that can we correctly go on to calculate its area.
Finally, let's zoom out a bit. Section 5, Classifying Triangles by Angles.
When studying geometry, you absolutely must remember this golden rule. In any triangle, no matter how weird or skewed or flat it looks, there are at least two acute angles. An acute angle, just as a refresher, is an angle that is strictly less than 90 degrees. It is structurally, literally impossible to build a closed three-sided shape without at least two of these sharp, narrow corners.
You can see how this plays out across the three distinct types of triangles. Take an obtuse-angled triangle, for instance. It has one massive, wide angle, but look closely. The other two angles are acute. Then you have the right-angled triangle, the star of today's explainer. It features exactly one 90-degree angle, forcing the other two to be acute. And finally, the acute-angled triangle takes it a step further, where all three of its angles are acute. But across every single category, that mandatory baseline of two acute angles is always there.
Which brings us to the end of our explainer. But before we go, I want to leave you with a provocative question based on what we've just uncovered. Since we just established that every single triangle in existence must have at least two acute, less than 90-degree angles, can a triangle ever mathematically or physically have two right angles? Think about the shape that would create, and what would happen to those lines. I highly challenge you to sketch it out and see for yourself. Thank you so much for joining me to explore the elegant logic of geometry today. Keep questioning, keep calculating, and I'll catch you in the next explainer.